Hello everyone, welcome back. Let us continue our discussion on reinforced concrete design. And we are in week 12 and this is our fourth lecture. So in this lecture, we are going to learn how to do model analysis of a structure. Now we have already modeled the building in StatPro and we'll do a model analysis there. But before that, let us first go through the basics of model analysis. Of course, as I told you earlier, that this is not a course on structural dynamics, so we'll not go into the details of mathematical theories, but of course we have to go through the basics to understand what we mean by model analysis, because in the following weeks also we'll do response spectrum analysis and time history analysis. So for that, let us quickly brief you about the model analysis. Now for that, let us first consider a frame. So you can see a frame here which has a beam at the top and it is supported by two columns. The stiffness of each column in the lateral direction is given by K and the mass of this beam is M. Now let us for the time being assume that these columns are massless compared to obviously the beam or the roof slab. We have a roof slab here that we idealize using this mass. Okay, so compared to that, the mass of the column is very less and hence we neglect it. Now, if there is a say ground motion, because our main objective is to design the structure against seismic forces. So if there is a ground motion is actually defined by the acceleration at the support level. So G stands for ground. So xg double dot is the acceleration of the ground that we measure at different locations using seismograph. So normally, if you look at the earthquake records, typically it looks like something like this. Right. So initially it starts from 0, then after certain time, the major portion of the ground motion due to the seismic wave, they arrive at that particular site. So say this is the main part of the ground acceleration, and after this, in this part, again it comes back to rest. Excuse me. Now, this initial part, it is called the built-up phase, and then this part is the strong motion phase for the earthquake. Now, the moment the earthquake comes, then this building starts moving in the lateral direction. So let us mark that by x, and it is a function of time. Obviously, if there is any earthquake, it also deforms or moves in the other direction, so that we can manage with the plus minus sign of x. So that's why we show this arrowhead in one direction, but as the time progresses, so there will be a plus minus of this displacement. Now, this structure has one mass, and therefore for this structure we can define the deformation of this frame using this x of t, and this is what is called degree of freedom. So DOF is called the degree of freedom, right? So what is the degree of freedom? It is the number of independent coordinates we need to define the deformed shape of the body. Now in this case 1 is enough, so this is called single degree of freedom system, so SDOF system. Now our main task is to develop the equation of motion, because we will see what we mean by this modal analysis. For that we have to write the equation of motion. So let us idealize this structure in a slightly different way. So this is the support, and we have the support motion, that is the ground acceleration is here. For the time being, our main aim is on modal analysis. So let us not focus on this. When we'll do the time history analysis, we'll come back to this. Now, we have a mass M that vibrates in the lateral direction. So this is M. The movement is defined by this x of t, and the structure has a lateral stiffness due to this column, and collectively both of them, so say K1 and this is K1, collectively they offer K as the stiffness. Okay, and then the moment the earthquake hits, it starts vibrating, and after the earthquake comes to rest, then still it continues vibration and finally it comes to rest. And that is because of the damping characteristic of the structure, which is defined by this sign, and C is the damping coefficient. Now, how to write the equation of motion? For that, let us draw the free body diagram of the mass. So the moment it tries to move in the horizontal direction towards right, there will be a spring force opposing that motion, and that is K times X. K is the spring constant, and there will be damping force also, and it is C times X dot. There are different damping models available. Let us not go into that details. That is not our objective of this discussion. Now, the moment it tries to move to the right due to some ground acceleration, there will be inertia force also, which is defined by mx double dot. And if there is a force, not this earthquake, for the time being, let us just assume that there is a force acting and that is causing the vibration. We can actually transform this ground motion into an equivalent force Ft, but that again, let us not worry for that. So if there is a force, obviously that force will come here, which is F of t. Right. Now we can write down the equation of motion, because this system of forces, they will be in equilibrium. So sum of all the forces equal to 0 will provide us the equation of motion, and that is mx double dot plus cx dot plus kx is equal to f of t. Now from your +2 calculus knowledge, you can identify that this is a linear ordinary differential equation. Second order, right? And x of t, that is the solution of this equation, will have two parts: complementary function plus particular integral, right? So for this complementary function, we have to solve the homogeneous part of these equations. That means we'll write the same equation, but the right hand side is equal to 0. And this is what is called free vibration. Why free? Because there is no force on the right hand side. But because there is no force, still we call it free vibration. Why there will be a vibration? Because of the initial conditions, right? So this is what we call damped free vibration. Why damped? Because we have this damping force. Now, let us first identify the initial conditions. Initial conditions are x at t equal to 0 is x0, and x dot at t equal to 0, that is the initial velocity, is x dot 0. So we need to define initial displacement and velocity, and then we can solve this equation. Now, for the modal analysis, let us ignore this damping part. Okay, so this damping force, if we ignore, then the equation of motion becomes mx double dot plus kx is equal to 0. So this is the undamped free vibration equations for a SDOF system. So this is the equation that we are interested today to see what we mean by this modal vibration. Now, we can rewrite this expression as x double dot plus k by m times x is equal to 0. And let us assume omega square is equal to k by m. We'll see what is the meaning of omega in a minute. So the equation becomes x double dot plus omega square x is equal to 0. And of course, we have two initial conditions. Now, let us rewrite this equation and see what we can conclude. For that, let us rewrite this equation as 2 dx dt times d2x dt2 plus 2 dx dt omega square x is equal to 0. So what we can write here, the first part dx dt whole square d dt of that is equal to minus omega square d dt of x square. Right? So if we integrate both sides, we get dx dt whole square is equal to minus omega square x square plus c. Right? Recall, you all have learned equation of pendulum. So this is the simple pendulum. You all have done simple harmonic motion. So this pendulum, if we apply a initial conditions, so this is the initial condition, then what happens? It starts vibrating on either side, just like the SDOF system today we have. Right? Now, this position is called the mean position, and from that it moves this direction, and the extreme point is having 0 velocity, and then again it comes back to the mean position and then moves toward the other side, and it repeats. Right? That was the equation of simple harmonic motion you all are familiar with. Today we have the same mean position, and then the structure vibrates on either side. So on one side it moves, it reaches its maximum deformation on that side, then the velocity is 0, and then it comes back and it moves over to the other side. So if the amplitude x is equal to a, then v, which is dx dt, is equal to 0. So if we apply this condition, what we get? We get 0 is equal to minus omega square a square plus c. That means c is equal to omega square a square. Right? And then we modify this expression. What we have is now omega square times a square minus square. A, just like for simple pendulum, this is the amplitude. For this vibration also, we have the maximum amplitude of vibrations. So dx dt is equal to what? It is omega times square root of a square minus x square. So if we rewrite this expression as dx divided by square root of a square minus x square is equal to omega dt, then we get, if we integrate, we have sine inverse x by a is equal to omega t plus phi, some constant of integration. And therefore, we have x, which is a function of t, is nothing but a times sine omega t plus phi. And this is exactly same what you derived in case of simple pendulum, right, in your plus 2 physics. So now, what is this omega? It is the frequency with which this structure vibrates on either side, right? So this is omega is equal to square root of k by m, and this is called natural frequency. So the natural frequency of the system is actually governed by the stiffness and the mass of the structure, right? Now, why it is natural? Because the moment we apply some initial condition and allow the structure to vibrate, then with this frequency, the structure will vibrate, and hence it is called the natural frequency, right? It is not the driving frequency. So this forcing function can have a frequency, and that is the driving frequency, which is not this frequency, obviously. So first we define natural frequency for a single degree of freedom system. We'll just see in a minute, if we have a MDOF system for the structure we have already modeled in STAD, that is a multi-degree of freedom system. So for multi-degree of freedom system, how we can derive, that we'll see in a minute. But first, we get the idea of natural frequency. Right. Now, if we plot the amplitude of vibration, so at t equal to 0, this first part is 0, but we have this phi, so it will be something like this, and this motion will continue. So x of t, and this maximum amplitude is a, right? Now, all of you know from your SHM that this is what we call the time period t, which is nothing but t is equal to 2 pi by omega. So for the building, if it is a single story and single bay that we can idealize using this SDOF system, then for that we'll have only one natural frequency, and we have only one time period. Just keep that in mind, because when we'll define response spectrum, we'll actually come back to this concept of time period, right? So it is actually not here at the 0 location, because if it starts here, so we have to go to this position, and it is here. Otherwise, we can start from this maximum value to here. This is also a time period. Or we can start from this 0 position, and then when it actually touches the 0 line again, so this is the time period. So now if you allow the structure to vibrate, it will vibrate with this time period, which is nothing but 1 by frequency f, and f is in hertz, which is omega by pi. So this is in hertz. So we get the idea of natural frequency if we have a SDOF system. Now, obviously, the question comes in our mind is that if we have a MDOF system or multi-degree of freedom system, how to deal with that? For that again, let us revisit the portal frame that we have earlier considered. But in this case, what we'll do, we'll have two stories. So the first one is mass 1 and second one is mass 2. Obviously, we need x1 of t and x2 of t to define the deformed shape, and hence it is a 2 degree of freedom system. And for each story we have, say, collective stiffness. We have two columns. Together they will provide a lateral stiffness of, say, K1 and K2. Now we can idealize following the same concept. So we'll have one mass here and another mass there. So this is M1 and this is M2. 2 degrees of freedom, x1 and x2. Then the first story stiffness we can idealize with the help of a spring, which is K1, and for the second story we have K2. Similarly, we have dampers to model the damping. So this is C1 and this is C2. Now, just for the completeness, if we have, say, force F1 and force F2, so we'll have F1 here and F2 there. Now, we have to draw the free body diagram for the first mass. So this is M1. For that, we'll have a spring force here, which is K1 times x1, and then C1 times x1 dot. Then on the opposite side, we have another spring. The moment this mass M1 tries to move on the right side by an amount of x1 and the second mass by an amount of x2, obviously this spring at the middle will have differential movement at the two ends. On the left end, here we have x1, here we have x2. So the net deformation is x1 minus x2 for this second spring. So times spring constant is the force. So K2 into x1 minus x2. Similarly, we have damping force C2 x1 dot minus x2 dot. And we'll have the inertia force. So let us mark it here. So M1 x1 double dot. And if there is a forcing function, so this is F1. Likewise, we can also draw the free body diagram for the second mass. Now, this mass, it has only one spring attached. So it is K2 times x2 minus x1, because the net force must balance. So it is the reverse of this deformation. Similarly, damping force is x2 dot minus x1 dot. And the inertia force here, m2 x2 double dot. And then if there is a forcing function, F2 is acting. Now if we apply equilibrium, for the first case we have m1 x1 double dot plus we have c1 x1 dot plus we have c2 x1 dot minus x2 dot plus for the spring force we have k1 x1 plus, or let me write here because we have to write for the second mass. So we have k1 x1 plus k2 x1 minus x2 is equal to F1. So now you can see we have c1 x1 dot here and c2 x1 dot. So we can combine these two. So we can modify this as c1 plus c2 x1 dot and then minus c2 x2 dot, right? Likewise, this k1 x1 and we have k2 x1 here, so we can add k1 plus k2 multiplied by x1, so we can simplify that. So let us do that. So k1 plus k2 times x1 minus k2 times x2, right? Now for the second mass we have m2 x2 double dot plus we have here k2, or let us write the damping force first, c2 x2 dot minus x1 dot plus k2 x2 minus x1 is equal to f of 2. So that is the second equation. So we have, so this is our first equation and here we have our second equation. Because we have a 2 degree of freedom system, we have 2 equations of motion. Now if we write down these equations, so we have m1 x1 double dot plus c1 plus c2 x1 minus x1 dot minus c2 x2 dot plus k1 plus k2 x1 plus, so this is actually minus k2 x2 is equal to f1, and then we have m2 x2 double dot plus, for x1 actually it is minus, so it is let us write plus minus c2 x1 dot plus c2 x2 dot plus, again it is minus k2 x1, so minus k2 x1 plus k2 x2 is equal to f of 2. So if we write in a matrix form, we have M1, M2, X1 double dot, X2 double dot, plus we have C1 plus C2, then minus C2, minus C2, C2, X1 dot, X2 dot, plus K1 plus K2, minus K2, minus K2, and then K2. Right. So symbolically we write M X double dot plus C X dot plus Kx is equal to F. You can see the same equation we derived for SDOF system. The only thing is, here we have a matrix equation, and the point to be noted, it is a coupled equation, right? So we'll see in a minute how we can decouple this equation and what we mean by modal frequency. But first thing is that again it is a ordinary differential equation, and for the complete solution, again, we have to find out the complementary function and particular integral. So if we write down the complementary function, that is the homogeneous part, the right hand side is 0. And for that, again, we have to define the initial conditions. So initial conditions are x at 0, that is say x0. Of course, as many degrees of freedom we have, that many displacement at t equal to 0 we have to define. So this is basically, in our case, it is 2 cross 1. And then x dot, which is x dot 0, again, in our case, it is 2 cross 1. So if we consider again the undamped free vibration case, so we have, this is the equation of motion, right? Okay. Now, for this coupled equation, first we have to uncouple. So for that, x is equal to phi of z is the transformation, and if we apply this transformation, we can uncouple this, and this is what is called the mode shape, right? So if you look at the equation, so for every degrees of freedom xi, we can actually propose a trial solution. So if we have, say, xi is the ith degrees of freedom, and for that we have ai sine omega t minus alpha, that is the trial solution. So for all I, in our case we have 2 degrees of freedom. So we can actually write down the trial solution. So now you see, the moment we propose this trial solution, this must satisfy this equation. So if you put this equation back, what we have, we can differentiate this twice. So if we differentiate twice, that is xi double dot. So we have to differentiate right hand side twice. So this omega will come out. So that will be minus omega square. So you can do that. And then if you put back, we will get minus omega square m times a sine omega t minus alpha plus k times a times sine omega t minus alpha is equal to 0. Right. So what we do, we differentiate this expression twice and put it back in the governing equation of motion. Now if we do that, obviously what we get is k minus omega square m. I'm not going to write the third bracket. Obviously it is there because this is a matrix equation. Then times a is equal to 0, right? Because this part cannot be 0. Now, if that is the case, we get this as a eigenvalue problem. So this omega square, this is the eigenvalues. Now, this phi is the mode shape. So phi is the eigen vector. You all are familiar with eigenvalue problem. So just look at this expression. We need to solve the eigenvalue based on the stiffness matrix and mass matrix. And in fact, when we'll do the modal analysis, you'll see we'll define this mass of the structure, which was not defined for the static analysis that we have already covered in the previous week. So the moment we define this mass for the entire structure, we'll see how to define it instead. And then we can do this eigen analysis and find out what is omega I. So that is the natural frequency. And corresponding to each natural frequency, we can find out what is phi I. And this is what is called. So this is omega I is the natural frequency. And corresponding to each omega I, we can find out this phi from this eigenvalue equation. So that is called mode shape. We also call it modal frequency. And hence this analysis is called modal analysis, right? So for this modal analysis, what we have to do, we have to define the mass and stiffness matrices, and then we do the eigen analysis based on mass and stiffness matrix. The eigen solution will give omega square. Square root of that is the natural frequency or the modal frequency, and corresponding to each modal frequency, we'll get the mode shapes. This mode shape is actually used to uncouple this governing equation. Let us see how to uncouple, and in fact, let us consider this equation, because we will also use this equation for response spectrum analysis, right? So now from the eigenanalysis, you know eigenmodes or eigenvectors are orthogonal. So each modal frequency, they are orthogonal. So what is the orthogonality property? For that, let us again revisit the original equation. So we have mx double dot plus cx dot plus kx is equal to f, right? This is a matrix equation. I'm not writing the brackets, but these capital letters actually indicate that this is a matrix equation. Now, to decouple this, we have to apply this transformation x equal to phi z. So this is the original coordinate, and after this transformation we get this z. This is called modal coordinate. So this is the original coordinate. Recall, we have already defined the degrees of freedom. Now, if x equal to phi z, obviously x dot is equal to phi times z dot, and x double dot is equal to phi times z double dot. So we can modify this equation. So we have m, in place of x double dot, we can write phi z double dot plus, then c, in place of x dot, we can write phi z dot plus k times x, but we replace that with phi of z. Then we have f. So now the original governing equation, which was in the modal coordinate, is now transformed into, it was in the original coordinate, is now transformed into modal coordinate. So the second equation you see here, it is in the modal coordinate. Now, if we pre-multiply both sides of this equation with phi transpose, so what we have, phi transpose m phi z double dot plus phi transpose c phi z dot plus phi transpose k phi z is equal to phi transpose f. Now, phi transpose m phi is a diagonal matrix of diagonal terms are 0 because of the orthogonal property, and phi transpose k phi, similarly, it's a diagonal matrix. No off diagonal terms are there. All off diagonal terms are 0. For the timing, let us assume that phi transpose C phi is also a diagonal matrix, which may not be always true, but let us for the time being assume. So in that case, we have, let us write MD Z double dot. MD stands for phi transpose M phi. Likewise, KD stands for phi transpose K phi, and CD stands for phi transpose C phi. So what we have, the equation in the modal coordinate Z dot plus KD Z is equal to, we call it FD. So now you can see this equation, because MD and KD, and also for the time being, let us assume that CD is a diagonal matrix. So this is a decoupled equation, and the right hand side you see we have phi transpose F, and this is called modal force vector, right? So originally this equation is coupled, but we have uncoupled that in this modal coordinate, right? Now What we can write, xi of t is equal to summation phi I zi of t, I equal to 1 to n. Let us write this as a small phi because that is a vector. So for all I equal to 1 to n, if we have n degrees of freedom, in our case we have 2 degrees of freedom, so this is I equal to 1 to 2. So we find out the solution x1 of t and x2 of t. But for that, you see on the right hand side, we need z1 and z2. These are the modal solutions. And what is the advantage of this? In the modal coordinate, you see, if I write down the equation for the nth modal equation. So in the nth modal coordinate, that means here it is a diagonal matrix. So if I consider, say, Zi, so we have MDI Zi double dot plus CDI Zi dot plus KDI Zi is equal to FDI. Now you see, this is again a single degree of freedom equation. Actually, we'll come back to this equation when we will discuss the response spectrum analysis, which is very important for the design of a structure against earthquake, right? Now, this equation again, you can imagine as the single degree of freedom equation that we have studied here. So for that, again, we'll go for undamped free vibration analysis. So that undamped free vibration analysis is what? If you write down this equation, MDI Zi double dot plus KDI Zi is equal to 0. Now from here, you see, we get omega I is equal to square root of KDI by MDI. So this is small mdi. Now remember, these are the ith modal mass and ith modal stiffness, and the same natural frequency you have already obtained from where? From this eigenanalysis, right? So we get this modal mass, modal stiffness, modal damping, and the advantage, as you can see, we can solve the structure in the modal coordinate where we have all the degrees of freedoms are uncoupled. So we can solve it as a Hausdorff system, and then we can appropriately combine them to find out the response in the original coordinate. So x1 and x2 are there in the original coordinate. That is actually represented by z1 and z2, which are in modal coordinate. And in the modal coordinate, they are Hausdorff system. So we'll use this property and we'll see how easily we can find out the equation using this concept. So what you have learned is that the meaning of natural frequency, that means if we have a structure like this one, if we apply initial conditions and allow it to vibrate, then the frequency with which the structure is going to vibrate is the natural frequency. That is the first point to be noted. Corresponding to each natural frequency, we can find out the deformed shape, which is here phi I, and that is what we call mode shape. And in fact, we'll solve in a minute the same building that we have modeled, and we did the static analysis using STAAD.Pro software. And for each natural frequency, we'll also plot the mode shape. We'll see how the structure vibrates in its mode, right? And finally, the main point why I discussed, we'll not go into the details because beyond that, you need to go through the theory of structural dynamics. The main point to be noted, which is very important from the designer's point of view, because we'll use a technique called response spectrum. Method. This is actually defined in IS code, and it has certain advantage. The moment we'll do that response spectrum analysis, I will explain what is the advantage. But the point to be noted from this discussion is that the original coordinate can be expressed in terms of modal coordinate, and the moment we solve the natural frequency and mode shape, we can use the solution of SDOF system in the modal coordinate to get the solution of the structure in the original coordinate. Okay. Now, let us see how we can do the modal analysis in STAAD.Pro. For that, one additional task we have to do. If you recall, earlier we defined the stiffness because we developed the model in STAAD using 3D beam element, as you have seen. And then once we develop the model with appropriate cross sections and material property, we applied static loads. So we applied the gravity load, we applied the floor load. We did not model the floor slab in our analysis because we kept it simple so that you can follow. You can actually add the floor model in your finite element analysis. But because we did not consider the floor slabs, we had to apply the respective loads on the beams, and for that we use the floor load given in STAAD.Pro to define the floor mass. We never actually evaluated the mass of the structure itself. We applied gravity load. From there, we identified the reactions also, if you recall, the support reactions. But today, first we have to define the mass of the structure, and that I will show you in a minute how we can do it in STAAD.Pro. So now let us move over to STAAD.Pro. So here you can see the model that we developed earlier. So now in this model, first what we have to do, we have to apply the mass of the structure, because for modal analysis we need the mass of the structure. Now you can see how many degrees of freedom we have. We have multi degrees of freedom system. Obviously, if you write down the equation, it is actually a coupled equation. Here one small thing is there. As you can see in the 3D rendering, we removed that beam, but two columns here, two columns are there. We have to first delete those two columns. That we will do in a minute. And then we will see how we can apply the mass of the structure and then do the modal analysis. These two columns by mistake was there, so let us remove it. It doesn't affect the design, but for the modal analysis we don't need these two columns. They are not there actually. Okay, so now we have the model, those two columns are removed, that is the entrance of the building, and if you see, we do not have any floor slab. Those were applied using floor loads. Okay. Now, Here are the different load combinations, not combinations, different loads that we used in our analysis. So let us go to the reference load definitions. So we add the mass, you see, that is the mass of the structure. So reference mass, we need this mass for our modal analysis. Now we need to define along y, and for this mass, because it is a scalar mass, so we don't need to define the direction, so we can remove that. And then we assign this mass for the complete structure. So now it is assigned. Remember, there is no floor slab, so we have to define the mass corresponding to floor slab again using the same way we did for floor load. So let us define the member load, and if you recall, it was 17 y. So we'll do it in a slightly different way today. So what we'll do, we can select the beams and we can apply. Right. So if we apply, it is applied to that beam, but we will not repeat the same way as we did in the previous class. We will do it in a different way. Here you can open the text file for this entire model, and there you can very easily modify and apply for the entire structure. You see here the reference mass is applied. So what we do, and these are the floor loads we applied earlier. You can see that minus 17 was the force. So let us copy these beam numbers and where we have to apply this floor mass, and then for this mass we don't need to apply that negative sign. So let us remove that negative sign. So now this is for the one story, and we can repeat the same for the other story. So first we selected one beam and we wrote this text file where we have the command for defining reference load, and then we modify very easily here. Once we go back to the main GUI, you'll see all these loads are applied, right? So here if you go to this reference load, and then if you select this, you can see these loads are applied appropriately. Otherwise, you have to select all the beams, and then the way we did in the previous lecture, we have to apply. So now let us, so the beam masses are applied. Recall there were walls on major beam and minor beam. Now we apply the floor mass. Okay. The same way, we first copy it, and the same way we apply, and it is now applied. So we have to repeat for the other floor. You can see one floor it is applied. Now it is complete. So we have all the reference mass defined. And this is a very easy way to apply the floor mass, because we have already done the static analysis, and we copy that series of commands from the text file, right? So now we define the load case as model. Because this is a model analysis. And then here we have to select the frequency and then modal calculations. The second one we have to select. And now we can remove these loads, dead load and live load, because today we will not do the dead load and live load analysis. We will only do the model analysis. And then again from this text file we can change the load number, because other two loads are not there. So the load case number should be 1. Here you see the load case number is 3 because the third load case was model. So if we save it here, it is changed to 1, right? Now the model is almost ready. So we have to define how many natural frequencies we have to solve, because this is aimed of system. We have large number of frequencies. As many degrees of freedom we have, that many natural frequencies we will evaluate, but the higher natural frequencies are not active or significant. So that's why let us first solve for 10 natural frequencies. So we can see the output file, and here in the result you can see the natural frequency. So if you select here, you can see the natural frequencies. Note these frequencies are in hertz. So the first natural frequency is 3.347. Now other details are also provided. So you see mass participation factor, you see here. Recall the modal mass we defined after we decouple the equations of motion, and if you add all the modal mass, you will get the 100% of the mass. But here you can see with the 8 natural frequencies that we have listed here, we have up to 67% of the modal mass. And then in the post processing we can actually see the results, right? Now normally we go up to 90 to 95% of the modal mass. So accordingly you can increase the number of frequencies and check whether you have the adequate amount of modal mass in your analysis. So here you can see the mode shape. So it is the first mode shape. So it is a lateral mode. Then you can change the mode here. So if you take the second mode, and here you can see it is a torsional mode. Because of the asymmetry in the structure, we have this mode. In fact, in the design, this is very important to consider. So when you design, you have to actually design it against torsion. Again, the third mode is a lateral mode, as you can see. So you can change the number of frequencies, and accordingly it will also change the mode shape. So you can go to higher modes, and of course this scale of this vibration is exaggerated, but these are the modal responses. So what we can do, we can increase the number of modes in our analysis, and then accordingly we can find out the solution. So let us rerun once more. And again, you can see the frequencies here. Now, of course, if you look at the values, there are a lot of closely spaced modes. These are very critical when we design a structure against earthquake. Now, here again, you can check the modal participation factor. It is still up to 67.45. So we can increase this number to cover. So we have to go beyond these 15 frequencies to cover the 90% of the modal mass, right? So that way you can solve the modal frequencies, and this is the modal analysis of the structure. So we can increase this number and redo the same exercise. That will give you more and more higher modes, as many you need to cover the significant modal mass, which is normally 90 to 95%. Again, here you can see it goes up to 9 Hertz, and here again still it is up to 67. It has increased, but still 67%. So we have to go beyond. Normally we go up to 20-25 Hertz frequencies to cover the 90 to 95% of the modal mass. Here we only have up to 7 Hertz. So you can repeat that exercise. So let us close here. In the next class, we will see the design of the structure. Thank you very much.